right, this is the last talk of this session, and Amos Robinson will be telling us about reactive systems in F-star.
Try speaking.
Yep, sounds good.
Yeah, can put it here.
Okay, more safety critical systems. So I'm going to talk about a embedded DSL I've been working on for specifying reactive systems in F-star. Reactive systems. Okay. Reactive systems are computer systems that are in constant interaction with their environment. The classic example is a plane. A plane has flaps and it's got air, and the air changes and it's got to react to the environment. It has very strong, very tight timing requirements. So if it goes wrong, things. Your other reactive systems are motorcycles, trains, cars, robots, also coffee machines. So I'm going to talk about a particular reactive system, which is a driver for a sensor, and it turns out that it turns up in a bunch of these other cases. So let's say we have a driver, and we have a thermometer, and we have a display. And the driver says to the thermometer, hey, give me a reading. And the thermometer says, yep, 25 degrees Celsius. And the driver says, okay, update the display to 25 degrees Celsius. Wait a second, and the driver says, all right, give me another reading. And the thermometer goes, nope, I'm dead. At this point, the driver can probably say, okay, we had a reading not long ago. It's probably not too far off 25 degrees Celsius. This will work. And it also tells the thermometer to reset. Wait another second, and the driver asks again, what's the latest temperature? Thermometer says, nope, sorry. At this point, we've run out of. We don't know what the temperature is anymore, so we need to just say, no, it's invalid. If we were implementing this system in the real world, we would probably write it in C, because we want to run it on a microcontroller. We don't want a garbage collector messing with the timing, and we've got to write it in a language we can run. But unfortunately, if we want to verify this system, writing it in C is not very good, right? We've got this, what looks like a sequential program here, but it's actually running concurrently with the driver and the timer and the sensor. So actually specifying this program and verifying it is not trivial. So the idea of approaching verifying these sort of reactive systems is to do the functional programming thing and say, well, instead of reasoning about this imperative mess, we want to lift up the logic to a pure function that we can reason about and just forget about the C code, right? So one way to do this is to implement a function sensor logic, which takes the stream of sensor readings and it returns a stream of statuses and booleans whether to reset the thing. So to call that from our C code, we would need to change our C code a little bit, but because C doesn't support streaming, but we implement our streaming function as a init function and a step function, right? And then every step of the C code, it's just going to call this step function and provide it more inputs. It's going to provide it the most recent sensor reading. So this is good because we've gotten our pure system that we can reason about. And we've taken our C code, which was not too complicated before, but difficult to reason about. Now we've got this little stub of C code that is not even worth verifying, right? It's trivial. So if we want to implement our streaming function we could implement it in a language like Lustre or in a synchronous language. So this is what it looks like in a synchronous language embedded in F star. And we say we're describing an age stream. The age stream says at every point in time, if the current sensor reading is valid, then the age is 0. The current sensor reading is good. Otherwise, we want the previous sensor age. That's what this followed by means. But we want the previous age incremented by 1, right? But at the very start of execution, there is no previous age, so we need to provide a default value to start with. So we say valid timeout followed by the age plus 1. And we do a similar thing for the status. So we can specify this program, right? One of the advantages of writing it in a pure functional language is that we can now specify what the driver should actually do. And one property that it should satisfy is probably that if our sensor logic gives us a reading and it says that this reading that we get is valid, then it should really be a reading that we got from the input, from the sensor itself, right? It shouldn't make up values. And furthermore, it should be a reading in the past. We can make it a little more precise by saying that also it should not be the most recent reading. So this is an okay specification. We can rewrite it as a streaming specification, right? So this is a property that says at all times this property holds. But we can translate that to rather than a property that holds at all points in the stream, we can write it to a stream of Booleans, which should always be true, like a safety property. And we can rewrite the property to say that we'll define the latest valid reading from the sensor read. And we say if the current sensor reading is valid, we take that value. Otherwise, we take the previous latest reading. Or if there's none, we just take the invalid, right? And now our property says if the status we get from the driver is valid, then the status agrees with our latest reading. So we can prove that this is true. We can prove that this holds of our driver that we wrote. And the way we prove it is by translating to a transition system. One way to prove it is translating to a transition system and then proving it by induction over the trace. And if we translate to a transition system, then we get something like this. It's not, this transition system isn't much different from the program we wrote, except that the transition system isn't as compositional as the streaming program that we write, right? We can take the streaming program and compose them together. All right. So this is a little embedded DSL in F star. It's very simple. It has values and variables and primitive applications. It also has this follow by for delayed streaming primitives. And it has a guarded form of recursion for streaming recursion. And let expressions and assertions for checking things. So we start with an embedded language in F star, and it desugars to a core language, which is intrinsically typed. Then we can translate to a relational transition system, and on that relational transition system, we can prove properties of our system. Our core language semantics refines the relational transition system so that anything we prove here holds here. Then we can translate to executable transition systems, which we can actually generate C code for, right? I've proved half of the refinement here, but it's the wrong direction. I mean, it should be equivalence rather than refinement, but I've only proved one direction of the equivalence. So it's a little embedded DSL in F star. We can write small programs and verify them and run them on real microcontrollers, which is nice. But at the moment, it doesn't have the support for abstraction is really lacking. I have the start of rely guarantee style contracts so that we can take programs and hide the implementation, but that's not baked yet. In an original implementation, I need common sub-expression elimination because the core language is equational. You can do equational reasoning on the core language, but it's a lot harder to do equational reasoning on the transition systems. So you really want to do common sub-expression elimination before translating to equivalence, before translating to transition systems. However, I originally had an applicative, shallow embedding applicative, where we could use pure functions from F star as worker functions in the language, but then you can't do common sub-expression elimination in F star itself. Yeah, that's all.
Thank you. Any questions from the audience?
All right, so since this is a workshop about types, I noticed that you had... All right, okay, so since it's a workshop about types, the specification that you're using was a function that returned a stream of bools.
Yep.
Can you make that a stream of types instead?
A
So I could
stream of
use type-driven...
sort of.
Yes.
Yes, good question. I tried and I ran into universe issues, but I can't remember exactly what they were. And for now, I just left it as stream of bools. Bit of a cop-out, but sometimes it's nice to have specifications that we can execute because we can check them at runtime that if we have a specification for how the hardware, like a brake actuator, is supposed to behave, then we can check that that the brake actuator is satisfying its specification at runtime. So restricting it to booleans is in some way nice because it gives you computable.
Cool. Thanks.
We can take one more question.
So when you describe the core language, you said that rec is guarded. So could you tell us more about the type system, clock system maybe you have?
Yep. So latest here refers to latest, but it's guarded by a follow by. So it's a really simple syntactic check. You just check that occurrences of latest only occur inside delays.
So it's a typical Lustre kind of syntactic discipline.
Yep, exactly.
And do you also have clocks in your language, or
No, not yet.
All right. So you plan to add this?
Yeah.
And a related question. So what happens if you define nodes? If you use a Lustre language, right? So you don't have functions, you have nodes. Do you do modular compilation or modular verification, or you just flatten out everything? And so like the fbys, do you compile them at the top level and to just bring all the nodes into one flat namespace and all these fbys becomes variables there, or do you have local variables?
At the moment, it is all flattened out. I've got contract support, or I'm working on contract support so that we can hide the implementation of nodes. But that's really more for reasoning than coding.
Thank you.
Yeah, let's thank the speaker again. Also give another round of applause to all the speakers in this session.